Hi, the aim of this talk is giving you some inputs regarding practical aspects in LIBS measurements. Before we start, it may be useful to remember the basics of the technique. As a laser beam is focused on the sample, the temperature of the zone locally heated quickly rises until exceeds a threshold condition called breakdown condition, inducing the plasma formation. The signal emitted during the subsequent cooling due to electrons recombination and atoms de-excitation can be registered, and from the analysis of the characteristic transition spectra, it's possible to obtain qualitative and quantitative information on the species inside the plasma.
LIBS uses a laser as both the sampling and excitation source, and the processes that are involved in a generic LIBS measurements are summarized in this image. Once a laser pulse of sufficient energy and appropriate duration is focused on a sample, this absorbs a fraction of the laser energy pulse, heating up. Once the appropriate conditions are reached, a part of the sample vaporizes into a plume, which is ejected. This plume continues to interact with the laser up to the point where a plasma is formed. This plasma expands, and after a short time, it starts to cool down, emitting the excess energy as both pressure waves and photons. The visible and UV emission is the one that is registered and analyzed in LIBS. In fact, since each element has specific emission spectrum in the UV-Vis region, due to bound-bond electronic transition, the light emitted by the plasma can be studied to obtain information about the composition of the analyzed sample, provided the plasma composition is the same as the samples. Now, it should be noted that not all the light emitted by the plasma is useful for a LIBS analysis. In fact, as shown in this graph, a large part of the emitted light comes from electron and ions recombination and non-specific transitions, which give rise to a continuum emission and cannot generally be used analytically. However, this continuum emission decays in time much faster than the specific emission from atom and ions. As such, it is crucial to register the LIBS spectra with an appropriate time delay from the end of the laser pulse.
A typical laboratory LIBS system is sketched in the figure. A pulsed laser, in this case operating at 1064 nanometers, produces pulses that are focused on the sample with a lens. The light emitted by this microplasma is collected with an optical system and sent through an optical fiber to a spectrometer, which possibly allows a broadband detection, typically from 200 to 850 nanometers. The spectral signal is then stored on a computer and analyzed using proprietary software. For some applications, such as in cultural heritage, the energy of the laser can be reduced down to about 20 millijoules, using neutral filters, with the purpose of minimizing the possibility of laser-induced surface damage of the samples. For further limiting the dimension of the laser spot on the surface, the laser beam is focused on the sample using a microscope objective. The combined use of low energy and tight focusing on the surface results in laser-produced craters at the surface smaller than 10 microns in diameter. The spatial lateral resolution of the LIBS measurements is one of the more interesting advantages of the technique. It corresponds to the dimension of the microcrater left by the laser on the sample surface. Here, a computer-enhanced enlargement of a typical laser crater is shown. Its diameter does not exceed 100 microns, which is practically invisible to the naked eye. Another appealing aspect of the technique is the possibility to perform stratigraphic analysis. Basically, the laser is used as a drill, focusing on the same position. Shot by shot, new material is ablated, and the corresponding spectrum carries information about this new layer. This is due to a specific property of the laser beam called depth of field, that ensures that it remains focused even beyond the precise focal point.
The choice of the laser is crucial for LIBS applications. Particular care should be paid to the wavelength as well as the pulse duration, as the laser-matter interaction is strongly dependent on these parameters. Several studies have demonstrated how laser sources emitting in the UV region tend to have high ablation efficiency, high reproducibility, high spatial resolution, and higher signal-over-noise ratio. At the same time, using wavelengths in the near infrared allows to lower the energy required for the ablation of the sample. In other words, the breakdown threshold is lower. Generally, the laser power is in the order of the megawatts, and as such, it can fairly easily generate a plasma on the sample. These power levels can be achieved by applying short laser pulses in the order of a few nanoseconds by an operation called Q-switching. The pulse length, defined as the fold width at the half maximum of the energy time profile of the laser pulse, mainly influences the fraction of energy that is transferred to the sample and the fraction of the laser pulse that interacts with the generated plasma. And it is also crucial in the plasma evolution processes. Various types of analyzers are commercially available, each one with its unique configurations of mirror, diffraction reticles, and prisms. While the basic principle is the same for all configurations, the light is spatially resolved and each component is registered separately, each system presents different advantages and limitations. The most used analyzers for LIBS are based on the Zerny-Turner and Eshel configurations. Once the plasma radiation has been spatially resolved, it is directed towards a suitable detector. As a general rule, the light detector is any device that is capable of converting the incoming photons into a measurable signal, generally a current or an electric potential difference. The most common detectors are photomultiplier tubes, photodiode arrays, or charge-coupled devices, or CCDs. This latter class, commonly found as an image sensor for digital cameras, is widely used in LIBS applications, often coupled with an image intensifier system and classified as ICCDs. In fact, the use of ICCDs allows time-resolved measurements of LIBS plasmas, which is a requirement in numerous LIBS experiments. Analyzers and detectors are almost often found integrated as a single system, which is set up by its manufacturer to best satisfy the needs of a particular application. Recent advances in electronics and miniaturization allow for the construction of small, portable spectrometers that still offer a wide range of capabilities. They can analyze the entire visible spectrum, as well as the near, IR, and UV in some cases, with high spectral and temporal resolution. Traditionally, to increase the LIBS performances, the approach chosen was to simply improve on the instrumentation, more powerful lasers, higher resolution detectors, and so on. However, in recent years, different approaches have been developed. One of the more common techniques is the so-called double pulse LIBS. In the most common configuration of double pulse LIBS, two laser pulses are consecutively delivered on the sample, separated by a suitable time delay, and the spectrum is registered after the second laser pulse. In this configuration, the second laser pulse interacts with the sample inside of a bubble of low-density environment generated by the shockwave of the first laser pulse. This allows for a lower absorption of the laser energy and a more efficient transfer of this energy to the sample. The result is a larger volume of ablated mass, a more energetic and persistent plasma emission. The resulting spectra reflects these effects, showing a significant increase in intensity and signal-to-noise ratio. Other double pulse configurations, such as the orthogonal configuration shown here, are possible but see limited use outside of the academic research. Another approach was very recently introduced by the group of De Giacomo, and it exploits the effects of deposition of noble metal nanoparticles on a sample to greatly improve the LIBS performances. While this partially restricts the LIBS advantages of not having to prepare the samples beforehand, the results more than compensate for the time and effort spent in this extra step. In brief, what happens is that the nanoparticles enhance the local and electromagnetic field generated by the laser pulse onto the sample surface. This is due to the oscillation of the surface conduction electron of the nanoparticles induced by the laser pulse itself. Moreover, the nanoparticles also act as thermally insulated effects, lowering the breakdown threshold and becoming ignition points for the plasma. This technique has proven to be very versatile and has been applied successfully to metal samples, gemstones, liquids, and for the detection of molecular bands. It is, however, not as simple as it may sound. The nanoparticle deposition, in fact, must be as homogeneous and pure as possible to obtain a significant effect. Moreover, the interparticle distance, particle dimension, and laser pulse energy are all critical factors for the obtainment of a good signal enhancement.
In this slide, we have summarized the most important advantages of the technique with particular regard to a rather delicate application. That is the analysis of unique and often valuable objects. With respect to other more established techniques, LIBS allows to achieve all the needed information in a single shot, and above all, this can be done directly in situ. Over the years, several different portable systems have been assembled due to the increase in requests for fast, reliable, and low-cost instrumentation for analysis. Recently, as you probably know, rather compact prototypes have been sent to Mars to analyze the surface on the red planet. This is the instrument we use in our laboratory, which allows to carry out measurements using a double PLAL configuration in situ while maintaining the performance of a benchtop instrument. Its main features are shown in the figure. So, let's take a look at the measurement procedure. As a simple case study, we have chosen a copper foil. The foil is placed in the sampling chamber near to the fiber optic that collects the plasma light. The focusing position is adjusted until the two red spots coincide. Then we have to set the laser parameters, such as the repetition rate of the flash lamp, usually 10 Hz, and the power of the flash lamp, which correlates the power of the laser beam. We choose the double PLAL configuration in this video, adjusting the delay between the pulses to 1 microsecond. For the acquisition, the spectrometer doesn't allow for a time gate lower than 2.5 milliseconds. Instead, the acquisition delay is set at 300 nanoseconds after the second pulse. When everything is set, we can start the measurements. How to manage a LIBS spectrum? Our system allows for a broadband range. Here we want to compare the performances of a single and double pulse. Our software, that is absolutely free and available for the community, allows us to look for a specific element of interest. In this case, we know that the foil is essentially copper, so we can trace the most intense copper lines in the single pulse spectrum, such as the two lines in the UV region around 300 nanometers. The intense lines in the infrared region, instead, are due to the elements present in the air, such as hydrogen, nitrogen, and oxygen. If we open the double pulse spectrum and compare the two, the enhancement of the signal is evident. This phenomenon affects the copper line but not the lines due to the atmosphere, thanks to the specific mechanism of the double PLAL configuration. Improving the signal to noise ratio allows for the clear detection also of the ionized copper lines in the UV region, as we can see here.
As previously mentioned, another approach to increase the LIBS performances is NLIBS. The usage of nanoparticles could be considered a limitation, in fact, as they add to the overall cost of the analysis, and if it is necessary to perform routine analysis, there is the need of relatively large volumes of nanoparticle dispersions to keep up with the demand. It is true that there are numerous retailers that sell noble metal colloidal dispersions with different geometries, size, and purity, but these might not be readily available or economically feasible for everyone. In light of this issue, we adopted a method to prepare the silver nanoparticles in-house for NLIBS using a relatively simple and cost-effective method. Essentially, we use the same system adopted for LIBS measurements as sketched here in the slide. A metal target, be it silver, gold, or copper, is immersed in an aqueous solution of a suitable stabilizing agents inside a cuvette, and the laser beam is focused on the target surface. In this video, we can see how the system works. The method is called Pulsed Laser Ablation in liquid. It is relatively quick, and with few milligrams of silver, we can produce several milliliters of nanoparticle solution. As the laser pulse ablates the metal target, nanoparticles are condensed in the liquid and stabilized by the stabilizing agent added beforehand. The procedure ends with the solution turns yellow, an indication that the nanoparticle colloid is formed, and also when the laser starts to get absorbed by the formed nanoparticles. To characterize the solution, a very simple method is to register its UV visible absorption spectrum. In fact, silver nanoparticles present a typical narrow peak in the region around 400 nanometers, depending on the average dimension of the nanoparticles. But how are these nanoparticles used in LIBS? For solid samples, in this case a copper foil, the procedure is simply the deposition of a few microliters of solution directly onto the sample surface. The droplet is then dried using a jet of hot air. Once the droplet is perfectly dried, the LIBS measurement can be performed. The whole procedure takes just a few minutes to complete. The LIBS measurement follows the same step of the traditional single pulse LIBS measurement. After adjusting the focus by overlapping the two red spots, the laser is armed and the pulse is triggered. Once again, we use our software to look at the spectra. We first open the single pulse spectrum and the one obtained with nanoparticles. Also, in this case, the enhancement is evident. However, our system is not perfectly suitable for this application because the maximum spot diameter is approximately 300 microns, and instead, a larger spot size should be preferable for LIBS. However, for the copper lines, the enhancement factor is around 2, depending on the specific line. Here, we can also see the silver lines as well. It is interesting to note that the hydrogen line becomes broader. This is an indication of the presence of an increasing in electron density thanks to the contribution of the silver electrons.
Before concluding this short lesson, we would like to show you a recent development of our instrument that brings the technique toward a new interesting application. Matching our system with a commercial microscope and 2 sets of step motors, it is possible to realize a scanner based on LIBS. In this case, we can scan surfaces up to 2.5 centimeters square with a resolution of few tenths of microns. So, take a look to how to realize the measurements. First, we have to select the area of interest for the mapping. Here we have chosen a brick sample with a peculiar heterogeneous surface, plenty of different clusters of clay and inclusions. To make the measurements, it is necessary to use a proper microscope objective that is strong enough for the laser beam, whose wavelength is in the infrared region. So, we also must adjust the focus, being the corresponding position in the infrared slightly different than in the visible. So, after adjusting the fiber optics, we have to adjust the focus position as well. So we are finally ready to realize the maps. An in-house developed software controls the step motors that are synchronized with the flash lamp of the laser system and the spectrometer trigger. Up and down, left to right, the laser beam scans the sample surface, acquiring step by step different spectrum. To show you the analytical capability of the method, we selected as test samples two mortars fragments from the Norman Adrano Castle in Catania, Sicily. The two samples consist in polished thin sections consolidated by epoxy resin. The mortars are generally characterized by a heterogeneous binder with the presence of aggregates due to volcanic ash with a large variation in grain size. The elements maps were acquired on a 50 per 50 matrix 2500 LIBS spectra with a lateral resolution of 100 micron for a total scanned area of 25 millimeters square. Once all the spectra have been acquired, an easy way to use the data is to select a representative line for each element of interest and report its intensity in grayscale. Each pixel is associated with a spectrum. The main elements present in the mortar are reported in the table, along with the central wavelength of the emission line used for building the compositional images from the LIBS spectra. From a geological point of view, it can be interesting to evaluate the ratio between different elements, such as calcium and magnesium, for instance, or building some false color maps associating a different element to the red, green, and blue channel. If you want to take into account all the studied elements, you can use some statistical approaches, such as a principal component analysis, that are able to reduce the number of the significant variables. To improve the results, we can perform an unsupervised self-organized neural network, such as a self-organizing map, called SOM. The SOM analysis is a distance-based clustering technique which can be used for classifying the surface point analyzed according to their elemental composition. You can find a complete explanation of the method in another lesson, specifically on this issue. One of the advantages of the SOM classification is that the classification takes into account only the elements which vary substantially between one cluster and the other. In this case, we use as inputs of the SOM algorithm the maps corresponding to the 11 major and minor elements detected in the LIBS spectra. In our case study, the SOM analysis identifies 5 different clusters. We can average all the spectra associated with the same cluster and compare the intensities of the lines of interest. The cluster number 3 corresponds to the epoxy resin, so it must be discarded. Now we can also achieve quantitative information using, for instance, the calibration-free LIBS method. So we move from 2500 spectra to only 4 to analyze. Comparing the concentration obtained with the calibration-free, we can find that the cluster 1 and 2 are very similar in composition, as are cluster 4 and 5 as well. Finally, we are able to build new maps that now show quantitative information.
We hope that this lesson has been useful for those of you who are now approaching the technique and are curious about how the measurement is made. What we have presented here is just an introduction about what can be done with this versatile technique. For any questions or clarifications, feel free to contact us.
See you soon!